Okay, now, ladies, we are going to start with the second part of our lesson, of lesson 1, which is the other two definitions of an acid and a base. Okay, if you remember last time, we spoke about Arrhenius acid-base definition, and we spoke about was in an acid, what is in a base as like properties that we already know. Today, we are going to continue the other two theories that we had to have in order to explain what is an acid and what is a base. Okay, the other scientist who came after Arrhenius is actually Bronsted-Lowry. And Bronsted-Lowry said an acid is a hydrogen or a proton donor. And as we can see, the difference between Bronsted-Lowry and Arrhenius is not actually a difference, because whether we said a hydrogen producer or a proton producer or a proton donor, it is the same. It means that you have this proton and you have this hydrogen and you are ready to give it up. Okay, but the difference in both of them actually arise from the base. As Arrhenius, we said we should have a hydroxyl group in the structure. So it's an OH minus producer, but Bronsted-Lowry said, or both of them, they said that it is an H plus acceptor. So this is where the difference comes between Bronsted-Lowry and Arrhenius. They do not, the problem is not in the acid. Both of them actually agree that an acid should produce or should donate a proton. The difference was in the base. Okay, an Arrhenius base should have a hydroxyl group in its structure, so it has to produce a hydroxyl group when dissolved in water or when solubilized or ionized. But Bronsted-Lowry said, no, it's not about the hydroxyl group that is going to be produced. It is about the proton that it is going to accept. Actually, the need for Bronsted-Lowry came when they studied ammonia. Ammonia is NH3. Ammonia, according to Arrhenius, is not an acid, because although nitrogen is a highly electronegative atom, but it is not willing to give up its hydrogen here. So this hydrogen is a non-ionizable, because it is actually not in an ionic bond. It's a non-ionizable hydrogen, so this is not an acid. But they found out when they did their studies, when they did the characteristics, the indicator, litmus paper, that actually when you put ammonia in an indicator like a litmus paper, it will actually give you the color blue. So the color is blue, which means ammonia is a base. So how? For sure, Arrhenius couldn't explain why ammonia is a base, because Arrhenius said it should be an ionic compound and it should be a hydroxyl group attached to a metal. This is how, and it should produce a hydroxyl group. Now NH3 doesn't have a hydroxyl group in its structure, so it cannot actually produce hydroxyl group. Okay, but Bronsted and Lowry, they found out that ammonia is actually, we will find out eventually, there will be a hydroxyl group, that ammonia actually is a base because it is a proton acceptor. So let's find out how. And ammonia actually is the only example that your book gives for a base that does not follow Arrhenius and actually follow Bronsted-Lowry definition. Okay, and when we do more practice, I might give you other examples, but in your book they only speak about ammonia. So ammonia, when it is dissolved in water, they found out that because of this high electronegativity of nitrogen, it is actually going to take one hydrogen from the water molecule, because we all know that water can be written as OH, H, which is H2O, and those actually can be given to the hydrogen, to the oxygen, so it will give us a hydroxyl group and a proton, and this proton is going to be attracted to the proton, to the 2 electrons of ammonia, forming ammonium. If you remember that you as well have done its Lewis structure when you studied the coordinate covalent bond NH4 plus the OH minus. So again, according to Prinstead and Lowry, a Prinstead-Lowry base is a substance or is a compound when solubilized in water or in any other material is willing to accept. It is a proton acceptor. It actually accepted the proton into its structure. For sure, this means that this compound should have a high electronegative atom, and this high electronegative atom for sure should have a free electron, so it can actually take this proton to it and give us the NH4. If you look at this equation, you will find out that eventually it actually produced the OH minus. But did it produce the OH minus? Because, and we cannot say it produces, because one who produces something should have the thing with them, right? But it doesn't have this hydroxyl group in its structure, so that's why we didn't say it's a hydroxyl group what producer. So again, according to Prinstead-Lowry, a Prinstead-Lowry base is a substance that is a proton acceptor. And the most famous example they always give is ammonia. Ammonia did not follow Arrhenius. That's why Arrhenius couldn't explain it. That's why we needed a theory to explain why some chemicals might behave as a base, although they do not have hydroxyl group in the structure. They do not produce a hydroxyl group because they have it in their structure. So Prinstead-Lowry came and they say, then an acid is a substance that is a proton acceptor. From where? From a water molecule, from any other molecule that actually has a proton and it's willing to give it. Maybe another acid as well. Okay, when we make a salt. So, did Prinstead-Lowry and Arrhenius actually had an argument about what is a base? No. Their argument was, what is an acid? No. All of their argument was about what is a base, and that's why the need arises for a new theory to explain bases, and the most famous base that Arrhenius wasn't able to explain, and Prinstead-Lowry were able to explain, is ammonia. Okay, as ammonia doesn't have hydroxyl group, so it's not a hydroxyl group producer, although eventually we found out that it is, but not from its own, but it was a proton acceptor, and we said this was because the nitrogen is a high electronegative atom, and it actually has an unshared pair that the proton is going to actually be attracted to, because it's positive and the electrons are negative, and that's it. Now let's look at the equation one more time. Or before that, let's see the definition of an acid. They say it is a proton donor. So if we take an acid that we know, which is HCl, and we put it in water, H2O, what is going to happen to the HCl? The hydrogen is going to be donated, right? Because we said, according to Prinstead-Lowry, it's a hydrogen donor. So it is going to be donated to what? To the water. Which is the same thing. If you remember in Arrhenius, this is what it was happening. HCl was solubilized. So in Arrhenius, let me do Arrhenius here. In Arrhenius, HCl in water is going to be ionized into H plus and Cl minus, and this H plus will go with water in order to give us eventually what? H3 H3O, which is a hydronium ion. The same thing happened with Bronsted-Lowry, because Bronsted-Lowry said that Bronsted-Lowry acid is an acid, is a substance that is willing to donate or a proton donor. So this proton was donated for the water in the form of a hydronium ion, and then we had the chlorine. I just want to make this a little bit neater. So we said we are going to have a Cl minus and a hydronium ion. Minus and H3O positive. Now let's see again. Oh. Yes. Okay, sorry. So let's see now again what we have. According to Bronsted-Lowry, HCl is an acid. Why? Because it is a proton donor. So what did water work here as? It was a proton acceptor. And according to Bronsted-Lowry, a proton acceptor is a base. Does water behave like a base? And if we put water with a litmus paper, is it going to make it blue? No, but we are following the definition. The definition says Bronsted-Lowry base is a substance that accepts a proton, and H2O, like how NH3 before, actually accepted the proton. A Bronsted-Lowry acid is a substance that is willing to donate the proton, and HCl donated the proton. So an H2O is a Bronsted-Lowry base. HCl is a Bronsted-Lowry acid. Now the thing that is connected to each one. H2O here is connected to the hydronium ion, and the HCl here is connected to the chlorine. Because if we said that this reaction is going in the opposite direction, we will find out that the proton now has to be given to the chlorine, right? Yeah, again, with this equation, okay, I will show you the two easy ways, especially when we do our practice. The chlorine is connected to HCl because chlorine came from the product of HCl. The hydronium ion is actually a product of H2O. So H2O and H3O or hydronium are connected. HCl and Cl minus are actually connected. Okay? In other ways, the real thing now, okay, which is the scientific thing. If we have to have this reaction to go in the opposite direction, then what should happen? The hydronium ion should actually give its a proton to chlorine. So what did the hydronium ion do? It is now working as an acid. Why it's working as an acid? Because now it is a proton donor. So here it is an acid. Chlorine, what did it do? Chlorine here actually accepted the proton. So it worked as a proton acceptor. So according to Bronsted-Lowry, it is a base. But to differentiate between the two, the ones in the product side, we add the word conjugate to them. So this is actually a conjugate acid, and this one is actually a conjugate base. So conjugate base, which is chlorine, conjugate acid, which is the hydronium. If you looked at the ones that we've connected, we've actually connected a base with a conjugate acid, which is, that's why it's conjugate, because the base should be connected to an acid. So this is the base and this is its conjugate acid. And we've connected an acid with a conjugate base, with the chlorine and the HCl. So again, According to Proust-Lowry, an acid is a substance that donates the proton. So HCl is an acid. According to Proust-Lowry, a base is a substance that accepts a proton. That's why water here, okay, acted as a base because it accepted the proton. This reaction to go in the opposite direction, the chlorine is going to accept a proton. So according to Proust-Lowry, it is a base. The hydronium ion now is going to donate the proton to the chlorine, so it is an acid. But we said we call this a conjugate base. And we call the hydronium a conjugate acid. Alright, okay. And then I told you the easier way to do this is to actually, instead of thinking all of this, the Cl minus is a product of HCl, so those two are connected. And the hydronium ion and the H2O are connected. So if H2O acted as a base, then what is connected with it should be the conjugate acid. If the HCl was an acid, so what is connected to it should act as a conjugate base. Now let's take another example. The same thing with an acid and a base. If we have H2SO4, which is sulfuric acid, it is still an acid for both Arrhenius and Proust-Lowry because both of them have a proton that are willing to be what? Donated. When we solubilize it in water, okay, those protons are going to be donated to water. For sure, if we are going to do this, we have to have two water molecules. Okay, so we are going to have SO4 minus 2, which is from the first one, plus 2 hydronium ions, 2H3O positive. If we are to name those ones, we will say H2SO4 was willing to donate the protons, so it is working as an acid. Water molecule actually accepted the proton, so it worked as a Proust-Lowry base. You can do it the scientific way or the same way. You will say the H2SO4 and the SO4 are connected. So if this is an acid, this will be the conjugate base. And the water and the hydronium ions are connected. So if this was a base, then this will be the conjugate acid. So what questions you might be asked? You might be asked to complete the equation of the ionization of the acid or the reaction of this acid with water, specify which one is the acid, which one is the base, and their conjugate acids and bases. Are they Arrhenius or Proust-Lowry? And the only thing that I need you to understand is that any acid that fits on Arrhenius fits Proust-Lowry as well. So you can actually say all Arrhenius acids are Proust-Lowry acids, and all Proust-Lowry acids are actually Arrhenius acids. And at the last part of this equation of this lesson, we are going to actually have another diagram where it actually shows all of the connections between the three theories. Now, let's do the same thing with bases. And we said the base that we need to speak about, let's say we are now going to speak about a famous Proust-Lowry base, which is NH3. Ammonia in water, it is a proton acceptor, so it will give us ammonium. And the water is going to lose, so it is a hydroxyl group, because we said water is actually HOH. So this proton is going to be lost to the ammonia. So ammonia here worked as a proton acceptor, so it is the base. Water here worked as a proton donor, so it is an acid. Right? And if you remember, we said in the previous example, is water a real base? No, it's not a real base, because it doesn't have any of the characteristics of a base. It doesn't change the indicator, it doesn't have a slippery, it doesn't have a bitter taste, it's not caustics and all of that. Okay, now if this is going to go in the opposite direction, then this ammonium should give its proton to the hydroxyl group. So actually ammonium is an acid because it is a proton donor. The hydroxyl is going to accept a proton, so it will work as a base. But here on this side, we call them conjugate on the product side. If we are going to say in ammonia and ammonium are connected, so if ammonia is a base, what is connected to it should be a conjugate acid. Water here worked as an acid and it is connected to the hydroxyl group. So if this is an acid, what is connected to it is a conjugate base. We can even do this to Arrhenius acids, to Arrhenius bases. Like if we have sodium hydroxide and it actually reacted with water, okay, then what, but nobody will actually ask you to do this, but let's try. Okay, now the sodium hydroxide, it's not actually all of it according to Prosted, it's actually the hydroxide. So we can rewrite this reaction as OH minus plus H2O. We have electrons, the hydroxyl group can actually take a proton. So what is going to happen is that this is going to be a proton acceptor, which is all of this, which H and OH is going to give us H2O. And the water here is the thing that is going to give us an OH minus. That's why nobody will ask you actually to write this equation, but in case you needed it. Now, let's put the sodium again. We will have the sodium here. So the sodium hydroxide worked as a proton acceptor, so it is a base. Water donated the proton, so it worked as an acid. This water is actually connected to the sodium hydroxide, so it is the conjugate acid. And the hydroxyl group that came from the water is going to be the conjugate base. Okay. Now, if we looked at those two equations, one time water acted, and it's very important for you to use this term. It acted as an acid with the presence of a base, and it worked as a base in the presence of an acid. So this substance that works as that has two natures in the presence of, and it can be as an acid, sometimes it can work as a base, which is mostly water. We call it an amphoteric substance. We call it an amphoteric substance. It doesn't recognize it, but it doesn't matter. So an amphoteric substance is a substance that can behave as an acid or as a base, and we found out that water actually acted as both. It's not necessarily to have the characteristics of the acid or to have the characteristics of the base, but it actually falls down in their definition. because water sometimes was a proton producer, a hydroxyl producer, it was a hydrogen donor, and it was a proton donor, and it was a proton acceptor. So when it does that, it's called an amphoteric substance, and actually water is a substance that did that in this thing. We have other substances actually that works as amphoteric, which we will speak about after, when we speak about the strength of acids and bases. Okay, so an amphoteric substance is a substance that can actually work as both. Now, so we are done with Arrhenius, we are done with Bronsted-Lowry. Now let's see Lewis. You know Lewis, he likes the dot structures, which he is fond of his electrons. So he has the broader definition of all, which is an electron pair acceptor and electron pair donor. So he said an acid is an electron pair acceptor actually. Okay, let me give you an example here so you can actually see it. And you need to understand that Arrhenius fills in Bronsted-Lowry definition, and we did that. And Bronsted-Lowry and Arrhenius, they fill in Lewis definition. So let's take one of them. Let's say HCl. HCl is an acid according to Bronsted-Lowry, because with Arrhenius, for example, it will give us H plus Cl minus. Or according to Bronsted-Lowry, when it reacts with water, it will only give the H to the H2O, the proton. So what happened to the electron of hydrogen? It was given to chlorine. So it was an electron pair acceptor. Why then HCl is an acid? Because it actually took the electrons of the proton to itself, right? A base is an electron pair donor. Like, for example, if we took ammonia, for sure it actually fills down for everything, but this is the easiest way for us to like understand it. What happened? This was HOH. It was willing not, but it's not a donor like those electrons are going away and not coming back. No, because those electrons were actually donated to the proton, right? So they were willing to share or donate those electrons to the proton here. That's why it is a base. It's an electron pair donor. Now, let's have examples that we would never ever think that they are acids or bases, but according to Lewis, they are. We have this substance which is called boron trifluoride. This is a boron substance which is in group 3. It is connected to 3 fluorine, you can say like atoms. They found out, you know, this substance, when it reacts with NH3, actually it likes this boron actually has the affinity to have more electrons. So it will actually go and take those electrons of the ammonia. But we already said, will ammonia actually give those electrons and not away completely? No. So what is going to happen? What is going to happen is we are going to have this compound. This is a coordinate covalent bond that we do as, if you remember, as an arrow. It is given to boron, and those are the 3 fluorine. And why this actually happened? Because fluorine has a high affinity for electrons, so it actually withdrew all of the electrons toward them, which made this boron actually wanting more electrons. So this is actually what happened. We wrote it as an arrow because this is how a coordinate bond is done, but you can as well put it as this. So this acted as a Lewis base. Why? Because it was an electron donor. BF3 worked as an acid. Why? Because it was an electron acceptor. So BF3 is an electron acceptor. Ammonia was an electron donor. BF3 was a Lewis acid. NH3 was a Lewis base. In other words, FBF3, it might not have any, let's say, characteristics of an acid, but they found out that it acts as an acid. So it is a Lewis acid. So let's revise what we took so far. What we took so far is that we have 3 definitions of acids and bases. The first one was Arrhenius. Arrhenius was very simple. You need to see it in the structure. Let's see in the same page. You need to see it in the structure. Okay? An acid should have hydrogen to a high electronegative atom. A base should have a hydroxyl group that is connected, that is in an ionic bond. Okay, then Bronsted-Lowry came and he made it a little bit broader. The acid is actually the same. They have the same definition. So all Bronsted-Lowry acids are actually Arrhenius acids. Okay, so if you are only speaking about acids, we can have Arrhenius and Bronsted-Lowry in the same circle. But if we're talking about acids and bases, no, actually Bronsted-Lowry, okay, had a broader one. And if you remember, water, according to Arrhenius, we can like somehow say it's an acid or a base, but Arrhenius mostly speaks about the real acids and bases. Anyways, now ammonia came for Bronsted-Lowry and they killed Arrhenius with its base thing. So we can write here ammonia and other things as well, and even water when it's becoming amphoteric and all of that, because water itself will not give the H+, will not produce the hydroxyl group unless there is something else with it. Okay, and then after that, and a broader one came, which is Lewis, and Lewis was broader in both the acid and the base. So we can say when we see this diagram, all Lewis acids and bases are actually, all Arrhenius acids and bases are Bronsted-Lowry, all Arrhenius acids and bases are Lewis because they are in it. But the one that is outside cannot be, and we cannot say all Lewis bases are Bronsted-Lowry bases. This can't be happening because something like PCl3, it cannot take a proton or accept a proton, but it is in Lewis, but it's not in Bronsted-Lowry, which we will speak about like next time when we do our examples. In the same way, okay, but the only thing between those two is the acid that is in common. All Bronsted-Lowry acids can be Arrhenius acids. And the other thing we spoke about was, what do we mean by amphoteric? And we gave an example of water. We said we have other examples. When we speak about the strength of acids and bases, we are going to speak about it. And an amphoteric substance is a substance that acts as both an acid and a base. Okay, and it was water here, for example, and water here. Once it was an acid with the base, and once it was a base with an acid. And then we said, what is a conjugate base? What is a conjugate acid? And then we spoke about Lewis definition, about the donor and acceptor of electrons. Now let's do this one to see what we are going to, if we actually summarize our examples. Okay. So H2CO3, it has hydrogen in the structure. It is connected to an anion. It can be donated, so it is an acid. Okay. Now, KOH, it has hydroxyl group, so it is an arrhenius base. HCl, it is an arrhenius acid. H2SO4, it is an arrhenius acid. C2H5COOH, it has a carboxyl group, so it is an arrhenius acid. Now, NH3, it is a Bronsted-Lowry base because it can accept protons, and it is as well a Lewis base because it can donate an electron. Now, Cl minus, by definition, it has electrons. So if something has electrons, it is actually willing to donate those electrons. So it is a Lewis base. And as well, if we put it in water, it is willing to accept a proton. So it is a Bronsted-Lowry acid. Base. So it is a base. So eventually, anything with a negative sign can be a base because it has electrons. A hydroxyl group is in the same thing. It has negative, it has electrons extras, so it can actually donate them, so it is a Lewis base, and as well it can accept a proton, so it is a Bronsted-Lowry base. Now, NH4 plus, it doesn't have electrons, right? But it's willing actually to give the proton, so it is an acid. Now for PCl3, I want you to think of it for when we are going to do our assessment, okay? Because I want you now to go to the periodic table and look at PCl3. Look where the P is. In which group? How many electrons does it have? What happens to its electron when it's with chlorine? Does it have a surplus of electrons? So can it act as an acid? Can it act as a base? Or it can act as both? Okay, so please think about this one and explain your prediction. This was our lesson for today. Okay, next time we are going to start with 19.2.